reducing agent. Then when we took a look here at the Ag, it went from +1 to 0, so therefore it gained electrons, didn't it? So it itself is reduced, so we say that that is the oxidizing agent. Now we took a look here at the NO3, right here and here. Do you see that it did not change any ion charge? So if it didn't change, then it's only a spectator ion. So therefore, it doesn't count. We don't care. So if I was to rewrite this as a net ionic equation, I would have the following. I would have Cu plus Ag plus giving me Cu plus 2 plus Ag, and I would now have the following ion charges. So far so good? And since we took a look at the start, this is the reducing agent, this is the oxidizing agent in the forward reaction. So we also introduced this idea that the reverse reaction is also attempting to take, hi. Oh, Cu0, yeah. Okay, the reverse reaction is also attempting. So we take a look here, the Cu going backwards, if it worked, gained electrons, so therefore it reduced. This would be the oxidizing agent for the reverse direction, isn't it? And if I have Ag going back in the reverse direction, it now is lost electrons, so it itself oxidized. This is the reducing agent. Are we okay with that so far? So we have a reducing agent for the forward, we have an oxidizing agent for the forward, we also have an oxidizing agent for the reverse, and we also have a reducing agent for the reverse. Now, here is the next statement you want to see. A reaction always proceeds away from the strongest oxidizing agent. So when we saw this reaction, we know that this reaction proceeded from left to right, but it did not go right to left. What this means is that this Ag is the strong oxidizing agent because the reaction proceeded away from it. This one here, because it did not successfully react to go in the reverse direction, is now considered weak, right? So similarly over here, since the reaction proceeded away from it, the Cu is the strong reducing agent. The Ag, since the reaction did not successfully take place, is the weak reducing agent. So the reaction will always proceed away from the strongest. Okay? Are we okay with that so far? So now at this point in time, when you now take a look, it is simply a matter of comparing the relative oxidizing agents from the standard reduction table. What the heck is that? So in this case, you're now taking a look at your data table and you're now going to the very last page. And you might want to now flip to that.
I don't like
Now, over here, first thing I want you to see is, do you see that on the left-hand side it says oxidizing agent, and on the right-hand side it says reducing agents? Okay, so I'm going to rewrite over here. I'm going to rewrite my reaction. So my reaction was Ag plus Cu giving me Ag plus Cu2 plus. So do you see that I have this Ag, which was the oxidizing agent, yes? Okay, and then in the reverse, the Cu was also the oxidizing agent. The Cu here was the reducing agent, and the Ag here was the reducing agent. So far, so good? Now, if I wanted to take a look, I wanted to see the Ag plus and the Ag. So over here on the left, I have my Ag plus and the Ag. Do you see that? So this is the equation I'm looking for. Now, I'm going to use over here a blue. So do you see that I have my Cu2 plus and my Cu? Do you see that? So down here, I've got a bunch of Cus, but do you see over here that this is my Cu2 plus and my Cu? So far, so good? Do you see the Cu2 plus? Cu2 plus. Edwin? Do you see the Cu? Do you see the Cu? Yes, good, excellent. Now, based on this now, I want you to take a look at the side thick arrow. Do you see strength of oxidizing agent? Do you see that? So do you see that there is Ag here and Cu here? Both of them, remember, we had identified as oxidizing agent. Do you remember that? Now, we take a look. Notice as we go to the top of the arrow, what is that saying about the strength? It is strong. The bottom over here is weak. So over here, we take a look. Did we not say before that the Ag plus here is strong and the Cu2 plus is weak? So far, so good? Now, let's take a look at the Cu and the Ag. So do you see the Cu and the Ag, which is over here? It's on the right-hand side. So this is the strength of the reducing agent. Do you see that? Now at the very top, what do you see? Weak. At the bottom, what do you see? Strong. So in this case, the reaction will always go from strong to strong. So if I have strong right over here, and remember we said that was also strong, and it's down here. Do you see as you go from left to right, right here, it's going downhill. When it goes downhill, it will react spontaneously. So if I start with these two here, they are both strong and strong. On this diagram, their relationship is strong to strong, it's downhill. A reaction will take place. So if I took a beaker and I put in Cu2 plus and I stuck in a piece of Ag metal, so now I have Cu plus 2 and Ag, will a reaction take place? So let's take a look. I'm going to use red. So Cu2 plus is here. Ag is up here. Do you see it's going from weak to weak? So going from left to right, it's going uphill. So does it want to go uphill spontaneously? No. So in this case, it's kind of this analogy. When you ride a bike, you like going downhill, yes? But it takes work going back uphill, yes? So that's the whole idea. Going in the red direction requires something to help it. So like when you were young, your parents would take you to the top of a hill, you go, whee! You go down, and then at the bottom of the hill, what do you say? Daddy, 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 push me up, right? Yes? Wasn't that your childhood memory? Sure. Okay? So in this case, now notice I keep on saying going from left to right, like how you read English sentence. Because could you not say this one, if I go from right to left, wouldn't that be downhill? technically. So therefore, I always specify going from left to right, going downhill is going to be spontaneous. Good? So, with regards to this, this is how you guys are going to use this chart to help you predict whether you're going to have a spontaneous reaction or not. Are we okay with that? Okay, so I'm going to give you some to try. Let me just pop back to the previous class. Okay, let's try these ones. Are these spontaneous? Yes or no?
Are we supposed to see it?
Alright, good luck.
Oh, okay.
CO plus CO2.
Sure, 50-50 chance. Okay, so again, when you take a look over here, you've got AG. Where's my AG? And then I'm taking a look at CO, so let me just find CO for you. So the CO is found right over here, and I am taking a look at CO2 plus, which is over here, and then I am looking for AG. So left to right, it's going to be uphill, so it's a no. Now, one thing I want to say is, it doesn't really matter if I wrote CO2 plus AG, or AG plus CO2 plus, they're exactly the same thing, okay? So never ever expect that I'm going to give you any clue based on how the sequence with which I'm writing it in the reactant side, okay? Okay, second one, PB and BA. Is it a reaction or no reaction? So that's a yes. So in this case over here, I'm going to look for PBBA2 plus. So BA over here, and then over here, I'm going to look for PB. Okay, which is right here. So if I take a look, it is PB2 plus and BA is definitely downhill. And so in this case over here, yes. Now, one of the things I want you to make a note of is, did you notice that this seems to be a bigger gap? Yes? Now, just as another layer is, the bigger the gap, the faster that reaction. So I want you to think about your bicycle. The higher the hill, the faster you're going to go down that hill, isn't it? And so that is going to have some sort of impact on how fast that reaction is going to take place and how much energy you produce, right? So in this case, when they actually make your batteries, they actually deliberately design the battery so that there's a certain distance. Now, you might say, well, why don't they have something that goes like from way up here all the way to down here? Wouldn't that be like a ginormous drop? And wouldn't I get a lot of energy? Yes, you would, but it would be very difficult to control. How many of you guys have heard of like the exploding Samsung notebooks way back when, right? And what had happened was that the battery was running too hot, and that's why it spontaneously blew up, right? So therefore, in developing batteries, there's always got to be safeguards, right? Even like right now, when you guys take a look, I told you guys about heat being the huge damager of your batteries. So one of the things that you guys want to think about, especially when you guys are eventually thinking about buying batteries, battery-driven cars, is the battery management system. And the whole point of the battery management system is how they keep the battery cool at a normal running temperature. Because if a battery runs too hot, then basically it will wear out the battery too quickly. right? This is one of the reasons why Tesla tends to be a little bit more expensive than some of the other cars because of how they configure their batteries, right? And we'll talk more about that in the next unit. Okay, CL and F2. So over here, we have F2, and we have CL, which is down here, and we've got CL minus and F2. So going down, yes, this one here is spontaneous. Now, why I wanted this one is because this is dealing with a non-metal. Okay? So, next one, NiMn2 plus. Is that spontaneous, yes or no? The answer is, no, it's not. Okay? Now, for the last one here, you've got CR and SN2 plus. Now, here is the thing that I want you guys to make a note of. You've got the CR and the CR3, which is great. What I want you to make a note of is, do you see the SN2 plus here? Now, do you see over here that I have this SN2 plus and this SN2 plus? Do you see those two? So one of the things that's going to be very important is for you to make sure that you find the correct pairing. Do you guys see that? Because if you don't find the correct pairing, you are going to get the wrong, conclusion. So I am looking for this one here, and this one here was CR3 plus and SN, and will there be a reaction? Yes? Oh, sorry. Oops. Oops. There you go. Yes. Okay. Okay. Here's my last one. Oopsie. Oopsie. What happened? Huh?
What you looking at?
That's funny.
Okay.
That's really
That's
funny.
crazy,
So
bro.
this is my last one, and see if you guys are able to figure this one out.
Wrong answer, wrong way.
That's crazy.
Okay, last one, number 6.
SN plus 2. C plus 2. What? Okay.
Let's find the right pair first.
Which CU? There's the CU, there's the CU. And I'm assuming it's this CU, right? Because it's plus 2, right? The CU here. And then there is the SN. You're coping, buddy. What did you get?
Right, so
Okay,
both reasons.
yes or no? You think so?
Alright, so it will be
So,
this
if we were to take a look at this one, I have SN2 plus to SN. So I'm going to look for that right here. So I have SN2 plus to SN over here. And then the other one is CU2 plus to CU plus. So that is this one. Now, first of all, notice that there's 2 CU2 pluses here. I'm looking for this one specifically, okay? So with that in mind, if I was to take a look, my reaction is between SN2 plus and CU2 plus over here. So moving this over here and here, SN2 plus and CU2 plus. will a reaction take place? Over the cliff. Is it downhill? Technically, yes. Face plant down to the bottom of the cliff. Gasso goes, Miss Chan's making a big deal out of it. This is probably why. There will be a reaction? There won't be a reaction? It is going down. But, wait.
There's no going back.
Huh?
There's no going back.
No, is it gonna be, they're both trying to be oxidizing agents?
Ah!
So then whoever's-
Notice that they're both on the same side. What do they both want to do? They want to be oxidizing agents.
And so
Right?
the stronger one becomes.
So they both want to be oxidizing agent, there's no reducing agent there. So here's the deal. In order for you to successfully go downhill, it has to go from one side of the arrow to the other. They cannot be on the same side, okay? Because they both want to do the same thing. So let me use the analogy of the Chinese family dinner. Both uncles wants to give money to each other. They go, no, I'll give you money. No, I'll give money. No. Nobody ever gives, both of them wants to give money, nobody ever receives. Transaction incomplete. Right? So in this case, both of these want to be oxidizing agents, they cannot. Right? One has to give, one has to receive. Right? That is what we're looking at. So this one here will never ever take place because it is written wrong. Because both of these want to be oxidizing agents, you don't want that. Are we good with that? Okay? So that is your spontaneous reactions. So going back to our notes, if you go back in here, let's take a look at the next part. So we've now dealt with this part. It says the strongest oxidizing agent is at the top and the weakest is at the bottom. Each oxidizing agent in the table has its reduction equation listed. We'll talk about this a little bit later on. It says a reaction will be spontaneous if the strongest oxidizing agent is above the strongest reducing agent. And so we have just taken a look at this in our last 6 questions. Okay, so hopefully this should make sense. You're going from strong to strong, downhill. Yeah? You look angry.
Not myself.
Why? Okay. So,
Understandable.
this is what we're taking a look, spontaneous and non-spontaneous. Okay, so again, we're now going to do a sample question, and the sample question gets you guys now to rank strong to weakest oxidizing agent. Okay, so here's the question. I want to see if you guys can do it. This is similar to the lab that you guys did last day. Good luck.
Blind space on phone. PB and RH.
PB to RH.
PB is somewhere here at the bottom, if I remember.
Give it to you.
No, that's RB.
That's, we're looking for PB and RH.
PB right here. Where's RH?
You obviously don't have to see
It's not. What?
The aim.
Am I blind? Am I RH? Is Miss Chan playing a trick on us?
I don't know.
It'd be funny if it was.
Main page, bro.
Bracha. That's RB. I don't need that.
I mean, it's not even like PT. Is PT up here? Introduction.
I see RD, yeah.
I don't see PT here.
Miss Chan tricked us.
I don't see PT here.
I don't see it.
Are we gonna?
Yo, I found it. It's
You
near
found
the
it?
bottom.
To the bottom? Okay, okay.
No, I think
None
we're
of these are on your standard reduction table. You
Yep.
have to figure it out.
yeah, I think
without
we're
that.
gonna
Yeah, we don't.
do like reactions.
The hard way.
So
Yeah.
PD versus PT will be reactions.
Reaction,
And
reaction.
RH will be
Tim, we have to
reactions.
think.
So PT,
Yes.
it's like pretty strong one, right? PT should be pretty
Pretty strong,
one.
yeah.
So everything will go down. And then RH will be a pretty lower one because I have no reaction with PD and PT. So what I assume is that when PD react with PT, it's reaction. So
Yeah.
it will be lower than the strong one. And then PD reacts with RH, it's no reaction, so it's above like the lower weak, what is it called? Strength. So I assume that the PT will be the largest, then we'll probably with PD and RH. Yeah, that'll be it.
Yeah, so it's basically the opposite of it,
Yeah, for
right?
sure.
So you find RH and PB and then you flip it to the other one, right? Is that it? Basically.
So it'll be PT, PD, RH.
Yeah.
That's the following order of strong to weak.
Yes. Miss Chen's just dancing.
Okay, I'm just trying to say it. Why are you mad at yourself?
To be fair, my entire body is sore.
Yo, you don't understand. No, I already got my answers, bro. There's nothing I need to do. I'm set. Are you done?
Yeah,
Reaction, no reaction.
yeah. It's a
Yeah.
yes, no.
What do you mean? Yes, there's only 2 boxes.
Yes,
We
no.
got, what do you mean? We got three items.
Where?
Ions, you say.
Isn't there 4? 5?
There's 5
Oh
answers.
my
The gray
god,
boxes
that's
you don't
so
do.
true, bro.
You don't do the gray boxes.
Okay.
Because they don't react with each other.
Yeah, you're
Two plus one
right.
PD.
Oh,
What the
oh
fuck
my
did you
god,
do?
oh my.
I said it's the opposite.
Smart.
Reaction and no reaction.
Yo, that's crazy.
I thought you had to figure it out, okay?
We're just talking about that sand twitch.
Alright, here we go. So, when we take, yes, Gazzle, I hear it. So, remember when we did the silver, so we did the silver over here, the silver and then the copper, we said that there is a reaction, it produces silver, metal, and the copper 2+ ion, yes? So that was like in our beaker, but we also said at the same time, so here's my copper, at the same time, there is an attempt for the reverse reaction to take place, but it's unsuccessful because one has to be spontaneous, the other one is non-spontaneous. So if we were to take a look, you would expect that there will be a spontaneous versus a non-spontaneous. So to figure this out, if I was to take a look at rhodium versus palladium, if I have RH2 plus PD going forward is not spontaneous, and now I have a corresponding PD2 plus rhodium trying to go backward, will there be a reaction? Yes, there would. So this one, I would say that there is a reaction. Does the logic make sense? So if I was to now take a look at the second one, where I want to analyze the PD2 plus, so if I look at the PD2 plus platinum, will a reaction take place? So now I'm going to go and take a look at the opposite, oopsie, which is platinum with PD. So PT2 plus PD going backwards. Is there a reaction? Yes or no? PT and PD, is there a reaction? PT2 plus and PD. Is there a reaction? Is there a reaction?
Maybe yeah.
Yes, there's a reaction. So there's a reaction here. So what does that mean for this forward reaction here? No reaction. So this one here is no reaction. Is the logic making sense? Okay. Now it says list the oxidizing agents in order from strongest to weakest. So question, which one's the oxidizing agent? These ones or these ones? So you have to now analyze this and go, okay, if I have this and it turns into RH, that means it gained electrons. It itself is reduced, making it the oxidizing agent, isn't it? This one is going from 0 to +2. So in this case, going forward, it loses electrons, so it's oxidized, so it's the reducing agent. So based on these, the ions here are the oxidizing agents right over here. So now doing what we just did in our lab last day, we go across and we see how many wins we have. This one I have 1 win. This one I have 0 wins. This one I have 2 wins. So therefore, PT plus 2 is greater than PD plus 2, which is greater than RH plus 2. Do you guys see that? So do you see the layers of thinking you guys are going to need to do here? Okay? If you identified it wrong, then you are going to identify the wrong oxidizing agents, and the entire question is wrong. Are we okay with that? Good? Okay. Right now it is 2:38. I'm going to give you guys 2 minutes of brain break, and then we're going to go into oxidation numbers. Okay? So you have 2 minutes. We will resume at 2:40.
Whoa, buddy, this is my problem.
Move for that shit, dude.
I'm moving for my problems.
All right.
Thank you.
Now for this next part, we're going to be introducing the concept of oxidation numbers. Now in terms of where oxidation numbers are concerned, they are similar to ion charges. But one of the purposes of oxidation numbers is that they are not necessarily real numbers. All that they are here for is to actually help you monitor what is going on with the electrons during a chemical reaction. It's like accounting. Okay? Now, in this case over here, when we're dealing with oxidation numbers, first thing we wanted to ask is what gets the plus and what gets the minus. Now, in this case, it says in oxidation numbers, the species that is more electronegative gets the negative number. And you're like, electronegativity? Yes, electronegativity. Do we have to deal with that chart? No, you don't. All that you care about in general is that when you guys learn about writing chemical formulas, the left one here has a tendency to be the more positive one, and the right one here has a tendency to be the more negative ones, right? Or on the periodic table, whatever is on the left-hand side tends to be the more positive one, and whatever is on the right-hand side tends to be the more negative ones, okay? Now, one other thing that I want to say, and later on with that, is if you have your periodic table like so, in general, the one that is closer to the top right is the one that is more electronegative. So when you're comparing two things like, let's say, sodium here, and let's say fluorine here, fluorine is closer to the top right, isn't it? Therefore, it's more electronegative. Okay? So let's say if I have potassium over here and bromine here, which one is closer to the right? Bromine, right? So that's what we're looking at. Now, where oxidation number is concerned, again, They are for the purposes of accounting. They might not necessarily be real. Okay? So in this case over here, when we deal with numbers, you may come across numbers that kind of look a little bit unconventional. And we're going to talk more about it. Now, there's a bunch of rules that you're going to need to follow. Now, do you need to memorize them all? No, you don't. So the more that you guys practice, the more that they're going to become familiar to you. But let me go through this just to explain them all. First one says the sum of all oxidation numbers in a species is equal to the charge on the species. So if I had something like sodium and chlorine, you know that the entire thing here has an overall charge of 0, yes? What charge is on the Na in sodium chloride? +1. What charge is on the Cl? -1. So notice when you take these two numbers and you add them together, what do they equal to? 0. So whatever the positive and negative numbers you have, they should add up to whatever charge is on the overall molecule. Okay, first thing. Oxidation of uncombined elements or in their elemental state is equal to 0. So remember when I said here is some copper wire? That would be your copper solid. What charge is on that, or what oxidation number is on that? 0, because it's in its elemental form. Its protons and electrons are equal. Okay? When you guys make silver metal, again, that would have an oxidation number of 0. Oxidation number of a monoatomic ion is equal to its charge. So if I had something like Cu2 plus or Cu2 plus aqueous floating around in solution, its oxidation number is going to be +2. Okay? In a binary, and this should not be combined, this should be a compound. The element with the greatest electronegativity is assigned an oxidation number equal to its charge in a simple ionic compound of the element. So binary here means 2. Okay? So if I gave you an example, like binary, let's say something like, oh, I don't know, LIBR. If I take a look here at my periodic table, and I look at Li, which is here, and Br, which is here, which one is closer to the top right? The Li or the Br? Br. So therefore, Br is going to be given the negative assignment for its oxidation number. So Br is going to be negative, but negative what? So in this case, as an initial guide, what I would look for is, oh, it says Br here is -1. Do you guys see that? So therefore, I will say that this is going to be -1, thus forcing lithium here to be +1. Okay? Now, these last three are going to be the ones you have to keep in mind, because generally they're probably going to be what you start with in your analysis. The oxidation number of hydrogen in compounds is +1. And that makes sense, because a hydrogen only has 1 electron, yes? You can only give away 1. However, when it's combined with a metal, it is -1. What do you mean by that? If I gave you something like HCl, Cl is -1, H is +1, isn't it? But if I give you something like Na and H, at this point in time, the H is going to now turn into -1, and the Na is at +1. Okay? So in this case over here, general rule of thumb. If an H is combined with a metal, it is going to be a -1. Okay? If it's with anything else, it will be a +1. Oxygen or halogen, so oxidation number of halogen is -1, except Cl, Br, and I when it's combined with oxygen or another halogen with a higher electronegativity. What? I thought things like Br is -1, Cl is -1. When is there going to be any other number? So here's an example. So if I gave you something like Cl and F. Now if I take a look at my periodic table right here, and I take a look at Cl and F, which one here is closer to the top right?
Fluorine.
It's going to be the F. Therefore, F is going to be given the minus. And so in this case over here, this is minus, therefore it's forcing the Cl to be a +1. Do you guys see that? Okay? And so if I gave you a halogen with either oxygen and typically basically something, another halogen with a higher electronegativity, then it's going to force it to be a plus. Now the last one over here is oxygen. Now typically oxygen is -2, and you guys are used to that. This is only if it is with anything else except when it becomes a peroxide. Now in general, when is it going to become a peroxide? When it is combined with something from group 1 or something from group 2, and we will deal more with that a little bit later on. Or a superoxide, which is -1/2. And you're like, -1/2? That's a fraction. I've never seen an ion charge that's a fraction. That's right, you will never see an ion charge that's a fraction because this is not an ion charge. It's an oxidation number. And remember, oxidation numbers are only for accounting purposes. They are technically not real. So in this case over here, when you're dealing with superoxides, again, this is with group 1. Now, how do we do this? So these three are typically the three that we start with first. So if I take a look here at CO2, how do I determine their oxidation numbers? So the first thing that I do is I deal with the one that is got the most fixed number, in this case oxygen. So oxygen over here is -2. There's 2 of them, so in total I have -4. Now in this case over here, for the carbon, it's going to be something plus 4 is equal to 0. Why? Because CO2 is neutral. So what must be the oxidation total here? This must be +4. Do you guys see that? So I now go back, I only have 1 carbon. So each carbon here has to be +4, and the oxygen here has to be -2. Okay? So let's take a look at the next one. So the next one is Cr2O7 -2. So again, if I take a look, where do I start? I'm going to start with oxygen again because it will typically have a -2. So I'm going to start over here. This is -2 times 7. Total is -14. Now the Cr over here is times 2. It will equal to something. So now something plus -14 has to equal to the overall charge of -2. So what is the Cr total going to be?
12 +
this will be plus 12. So therefore, 2 times what is equal to plus 12? Plus 6. So the chromium is plus 6, and the oxygen is minus 2. Do you guys see that? Okay, so I would like you guys to try number 3, 4, 5, 7, 8, 9, and 11. Good luck. When you guys are doing your assigning of oxidation number, make sure you have a plus and a minus. Do not just go, oh, just a 3. Okay, because at this point it's like, did you mean it was a minus or did you mean it was a plus? This is about communicating clearly. Okay, so the next one. Let's go with Zara. Do you have that one?
Number 4.
Number 4.
H1 plus 1 and plus 5 and
What is it?
plus 5
Okay, and
minus 2.
did you guys get that? Okay, so again, we start off with what is known. So oxygen is known, so it's minus 6. Hydrogen is also
Plus
known.
3. Did you get
So
that?
therefore, this is a plus 1. So
Okay,
again,
well,
if you take a look, we start with what is known. So therefore, we get the plus 5, and that is our nitrogen. Okay, excellent. Number 5, what do we have? Let's go to Tom.
Okay. Plus 2 and minus 1.
You sure? When is oxygen ever a plus?
Oh wait.
I'm trolling you.
Yeah, she's trolling. She's trolling.
Wait, I
Because-
get it wrong.
So,
Where is it?
here's the thing. If you take a look at
not wrong, though.
oxygen, if you take a look at the difference between oxygen and fluorine, which one is closer to the right? Fluorine, right? So if that's the case, then fluorine is assigned the negative, oxygen is forced to be the positive. So therefore, that arrow is really important, right? So over here, when we take a look at this one is minus 1 times 2 is minus 2. Therefore, this is forced to be a plus 2. Okay, let's take a
How's
look
that? Yeah.
here at this one, which is
She
number
actually made me stare a
7.
bit as I did it.
Let's get Jacqueline.
I like how she's not doing this on her. She's just doing it.
I is plus 3,
And CL is minus 1.
minus 1. Excellent. Did you guys get that? Good? Okay, so again, going back over here, if I take a look at the difference between I and CL, notice that I is down here, CL is up here. Which one is closer to the top right? I or the CL? The CL. Therefore, it's assigned the minus. Okay? So here, if I take a look at my notes over here, this is going to be minus 1 times it by 3 is minus 3. So this one here has to be what? In order to make it equal to 0, it has to be a plus 3. Now, if I take a look at this next one is minus 2, thus forcing the carbon to be a plus 2. So now, in this case over here, what I want you guys to see is, see how this first one, my carbon is a plus 4. Do you guys see that? And this one now, my carbon is a plus 2, showing that the oxidation numbers could change. So for this next one over here, if you guys take a look, the next one here is Cl and F. So going over here into my data booklet, I have Cl and F. Which one is closer to the top right? It is F. So therefore, going back into my notes, therefore F over here is given minus 1, thus forcing Cl to equal to plus 1. Are we okay with that? Okay, so I have the last one. So So the last one is minus 2 times 4 is minus 8. So in this case, what am I going to have over here? And this one over here is going to be a minus 3. So P over here has to be a plus 5. Good? Now I'm going to do 2 more. So let's jump over to this one here. Now this one is a little bit crazy because there's so many things involved. So the hint I'm going to give you is that we will utilize the fact that you know what SO4 is. Because if you take a look at your data booklet right here and you look for SO4 in your data booklet, you see that SO4 is a minus 2. Do you guys see that? So therefore, if we go in here and we say that this is overall minus 2, what this will then say is for the VO2, this is going to be plus 1. So as a result, this is minus 2 times 4 is minus 8. S over here plus negative 8 is now going to be plus 6 to give me minus 2. Are we okay with that? Now if I go down here, this is minus 2 times 2 is minus 4. So the V over here has to now add to plus 1. So therefore, this is plus 3. Have y'all copied it down? All right. Shall we move on?
No.
No? Why not?
Because it's wrong.
Yes, Gazel?
We got like 4 minutes. How are we gonna move on? Well, we can do it last.
Well, you have 3
We can do this.
and
one.
negative 4. Isn't
I'm
that equal to
curious.
1?
You know what? Let's do simple.
Ah.
Because I'm
So
curious on
a
this.
lot of you guys right now probably just copy down the plus 3 and go, yep, that makes sense. Because 3 and the minus 4, I get 1. But I care about the fact that it's a plus 1, yes? So what should the V be?
Mm-hmm.
It should
It's
be
manageable.
plus 5.
No, good. If you leave out the
So if you
That's
guys
what you're
just
saying.
copy down the plus 3,
I got it right. Sure you did.
bad. Okay, last question. This one. Number 12. Now for this one, so far everything that we have done, we always start with the oxygen. So if I did this one, you're like, okay, let me start with the oxygen. This is minus 2 times 2. I get minus 4. So over here, this is going to be plus 4. So something times 2 is equal to plus 4, and it's a plus 2. If you do that, the moment you see this, you